Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning. Today we will focus on crystal formation and how ordered mineral structures develop in nature. I will describe the physical and chemical controls on nucleation and growth, give concrete examples from igneous, hydrothermal, and evaporitic settings, and consider why crystals record growth histories. At its simplest, crystal formation is the process by which atoms or ions arrange into a repeating unit cell to make a lattice. The process has two main stages. First, nucleation and then growth. Nucleation requires a system to reach a state of saturation or supersaturation. In solutions, this means the dissolved concentration exceeds the equilibrium solubility. In magmas, this means cooling reduces solubility of minerals. There are two nucleation pathways. Homogeneous nucleation happens within a uniform phase, but it requires a high energy barrier. Heterogeneous nucleation occurs on surfaces and is far more common in nature because surfaces lower the energy barrier. Once nuclei form, the rate of crystal growth depends on temperature, pressure, chemical gradients, and importantly on ion mobility. High ion mobility allows atoms to reach growth sites and produce well-formed crystals. Consider pegmatites as a case study. Pegmatites are late-stage igneous pockets rich in water and other volatiles. Pegmatites produce exceptionally large crystals because high volatile content increases ion mobility and favors growth of fewer large crystals. In contrast, rapid cooling and a basaltic flow produces many small crystals because nucleation is rapid and space for growth is limited. This is why basalt is fine-grained, while slowly cooled plutons yield larger crystals. Hydrothermal systems form crystals when hot fluid moves through fractures and cools or reacts with wall rock. Quartz veins in many gold deposits are a classic example. Minerals precipitate on fracture walls and can incorporate metal sulfides as inclusions. Evaporitic environments provide another pathway. When saline water evaporates in a closed basin, halite and gypsum precipitate. The crystal habit of halite can be cubic, and the size relates to evaporation rate and ion concentration. Crystal habit and morphology reflect anisotropic growth rates along different crystal faces. If one face grows faster, the resulting crystal will be elongated. Environmental factors such as impurity absorption can modify these rates. Zoning within crystals is a useful record. For example, growth banding in amethyst from geodes reflects changing concentration of iron and changes in temperature or redox conditions during growth. Twinning and epitaxy are also important. Twinned crystals result from specific symmetry operations during growth, and epitaxial overgrowth occurs when one mineral grows on another with compatible lattice structures. Kinetics and thermodynamics both matter. The most stable phase at given conditions may not form first. Ostwald's rule tells us that metastable phases can precipitate before the stable phase because of lower kinetic barriers. Fluid inclusions trapped during growth preserve temperature and fluid composition data. These microscopic pockets are invaluable for reconstructing the conditions of formation and for exploration purposes. To summarize, crystal formation is governed by saturation state, nucleation pathways, ion mobility, and space and time available for growth. Examples from pegmatites, hydrothermal veins, and evaporitic basins illustrate these principles. Understanding these processes helps us interpret mineral textures and guides exploration for economically important minerals.
Listen again to part of a lecture, then answer the question.
Pegmatites produce exceptionally large crystals because high volatile content increases ion mobility and favors growth of fewer large crystals.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.